Welcome back everyone. In this video, I will be discussing how we can use rate over time graphs to represent how an equilibrium system responds to change. Now, you should have seen a rate over time graph before. This was the one that was plotted when we did the trading game at the very start of the topic, so the game between A and B. And you can see the change in the rate of the forward and back reactions as the system starts to approach equilibrium. And when equilibrium is reached, that's when the rate of the forward reaction equals to the rate of the back reaction, as shown in the graph here. So one main difference between rate over time graph and concentration over time graph is that you can only have two curves on the rate over time graph, one for the rate of the forward reaction and one for the rate of the back reaction. Whereas in the case of concentration time graphs, you can have more than two curves depending on how many species are present in the system. Another concept that we need to reference in this video when we talk about rate is how do we actually change the rate of a reaction. And obviously this is linking back to collision theory, but for example, and you should have seen this diagram when we did chapter 7, reaction rate. But if you want to increase the rate of a reaction, you either increase the frequency of collision or you increase the proportion of collision with sufficient energy to overcome the activation energy barrier. So any factor that affects reaction rate has to fall into at least one of these two categories. Obviously, in this case, temperature affects both. So temperature would affect both the frequency of collision and the proportion of collision with enough energy to meet the activation energy barrier. That's such a mouthful. So whenever we talk about rate, you need to really think about collision theory. Anyway, so I'm going to go through the same 6 changes that we have discussed when we talked about concentration over time graph, and I'm just going to put rate over time graph into those changes. I don't even know what I'm talking about anymore. Let's just start with change number 1. So I'm still going to use the Haber process or production of ammonia, and this is just a quick recap. Change number 1 is that you adding some nitrogen to the system. So the system is going to shift forward or to the right to partially offset this change. And this is the concentration time graph that you should have seen. You can clearly see that there is an increase, a sharp increase in the concentration of nitrogen only. And as the system shifts forward, the concentration of nitrogen gradually decreases, but it is still higher than the original. So if you need to plot a rate of a time graph to represent this change and the response, so we're going to start with the equilibrium. So I'm just going to color code. So forward reaction, the rate of the forward reaction is going to be red and the back reaction will be blue. So before the change is applied, the system is at equilibrium, which means that the rate of the forward and back reactions will equal to each other. So your starting point has to be something like this. So notice how with the concentration time graphs, the concentrations of the species don't have to equal to each other. They just have to be constant to represent equilibrium. In the case of a rate over time graphs, you need to have the rates of the two reactions equal to each other to represent equilibrium. Now, if you draw this properly, the two lines have to perfectly overlap, but I really want you to be able to see both colors, so I did make them one a little bit higher than the other, but in real life, they probably perfectly overlap, or close to perfect. Okay, so the change in this case is an addition of nitrogen. Now, if you think about it in terms of collision theory, if I add nitrogen, that is going to increase the frequency of collision between nitrogen and hydrogen. So it really only affects the rate of the forward reaction because nitrogen is only a reactant for the forward reaction. Adding more nitrogen is not going to affect the rate of the back reaction because really it's only the frequency of collisions of the reactants that can affect the rate of a reaction. So what is going to happen the moment that you add extra nitrogen is that there is going to be a sharp increase in the rate of the forward reaction, whereas nothing has happened to the rate of the back reaction at this point because you have the same amount of ammonia or NH3 and the same level of collision. Now, the system will shift forward to respond to this change, and as the system shifts forward, nitrogen and hydrogen will be used up. So if you are reducing the amount of nitrogen and hydrogen, you would also gradually reduce the frequency of collision between these two species, and that is going to gradually reduce the rate of the forward reaction. So the forward reaction will have a sharp increase in reaction rate as the change is applied, and then it's going to gradually decrease because the response is that you have more forward reaction and you reduce the frequency of collision between the reactants. Now, at the same time, because the response is to have more forward reaction, more NH3 is going to be produced, and that is going to increase the frequency of collision between NH3 molecules because you're producing more reactants for the back reaction. And so that is going to gradually increases the rate of the back reaction. So you're going to have the back reaction increases in rate. And obviously, eventually, when equilibrium is reestablished, which is this part, you're going to have the rate of the forward and back reactions equal to each other again. Notice how the rate of this new equilibrium is higher than the rate of the original equilibrium, and this is because overall you have added more particles into the system, so you should have a higher frequency of collision overall, therefore you should have a higher reaction rate overall. I'm gonna just delete that so you can print it out if you want. So that's change number one. Similarly, if you go to change number two, which is a removal of a species, so the change here was that we have removed some hydrogen from the system, so the system is going to shift to the left to partially restore this hydrogen that is lost, and this is the concentration of a time graph. You can see a sharp decrease in the concentration of hydrogen, and then it's increased again, but it's still lower than the original amount. So if you think about it in terms of a rate of a time graph, once again, before the change is applied, system is at equilibrium. So you have the rate of the forward reaction equals to the rate of the back reaction. When I remove hydrogen, what it is going to do is it is going to decrease the frequency of collision between nitrogen and hydrogen. So once again, it is only going to affect the rate of the forward reaction because hydrogen is a reactant for the forward reaction. So that is going to cause a sharp decrease in the rate of the forward reaction. So the rate of the forward reaction will go down sharply, and as of now, you haven't affected the rate of the back reaction yet. The response is that the system will shift backwards, and as it does that, nitrogen and hydrogen will be produced because you're going back. So if nitrogen and hydrogen are being produced, the frequency of collision between nitrogen and hydrogen would increase, which gradually increases the rate of the forward reaction. So the forward reaction has a decrease in rate and then it gradually increases. At the same time, because the response is to have back reaction, you are using up ammonia, which means that you decrease the frequency of collision between ammonia molecules, which would gradually decreases the rate of the back reaction. And then eventually, as equilibrium is re-established, the rate of the forward and back reactions are once again equal to each other, but this rate will be lower than that of the original equilibrium because overall you have removed some particles from the system, so you should overall have a lower level of frequency of collision. So that's change number two. I think one and two actually the easiest. You can clearly tell what has happened just by looking at this because the change only affects one rate and not both of them. It gets a little bit more interesting when we talk about pressure. So change number three is an increase in pressure, and remember that if you increase the pressure and you have a gas system, it is going to increase the concentration of all three species in the system in this case. And the response is that the system will shift to the side with less moles to partially reduce the concentration. So you're going to see a sharp increase in the concentration of all three species. And then because in this particular case, the system shifts forward, two of them will go down and then one stay up. I do think that the rate of a time graph can explain why the system shifts forward in this case a little bit better than concentration over time graph. So let's just think about what it actually looks like. So once again, before the change, system is at equilibrium, so you have equal rates between the forward and back reaction. Now, if you increase the pressure, because you're increasing the concentration, you are increasing the frequency of collisions for both the forward and back reactions. So both of them will have a sharp increase in reaction rate. However, the effect of pressure is not going to be the same on the rate of the forward and back reactions. The forward reaction is going to benefit more from this increase of pressure because the forward reaction has more particles in the first place. So if it has more particles, because it has 4 particles compared to the back reaction, which has 2 particles on the reactant side, if it has more 4 particles, it is going to have a more significant increase in the frequency of collision when you increase the pressure. So what you're going to see is that the forward reaction has a significant increase in rate. The back reaction also has an increase in rate, but it's not as high as the forward. This is just because of how many particles are present in the reactants between the forward reaction and the back reaction. So as the system responds, and the system responds by shifting forward, once again, nitrogen and hydrogen will be used up, so there will be a gradual decrease in the concentration of nitrogen and hydrogen, which would decrease the frequency of collision and the rate of the forward reaction. And at the same time, you're producing ammonia, so that is going to increase the rate of the back reaction. So I think with the rate of a time graph, you can see that because the forward reaction is benefiting more from an increase in pressure, because the forward reaction uses more particles as reactants, it would make sense that once this increases, it has to go down, and if it wants to go down, then the response has to be go forward. Anyway, and then of course, once equilibrium is re-established, the rate of the forward and back reactions are equal to each other again. But it is very important to keep in mind that this new rate has to be higher than the original because you have increased the pressure. So overall, it should increase the rate of the system. So that's change number 3. Anyway, change number 4 is the opposite of that. So if I decrease in pressure, system will go to the side with more particles if we use Le Chatelier principle, and this is the concentration and time graph for that. So if I plot a rate of a time graph, once again, we start at equilibrium. So if you decrease the pressure, that is going to decrease the frequency of collision for both the forward and back reactions. So both forward and back reactions will experience a decrease in the rate of reaction. However, because the forward reaction normally uses more particles as its reactants, it is going to be affected more by this decrease in pressure. So there will be a more significant drop in the frequency of collisions of the forward reaction. So the forward reaction is going to go down more, whereas the back reaction doesn't go down as much, but both of them have to experience this decrease. So the response is that the system will shift backwards, and if the system shifts backwards, that's going to increase the rate of the forward reaction and decrease the rate of the back reaction. So you're going to see something like this. So eventually the system re-establishes equilibrium, but the rate of the system at this point has to be lower than that of the original equilibrium because overall you have decreased pressure. Okay. Now, you can also use the rate over time graph to explain why an equimolar system is not going to respond to a change in pressure. So if you look at this system, which is equimolar, you have 2 particles on the reactant side and you have 2 particles on the product side. So let's say you have equilibrium. So you start at equilibrium, which means the rate of the forward and back reactions are equal to each other at this point. If, say for example, I decrease the pressure, once again, that is going to decrease the rate of both the forward reaction and the back reaction. But they are going to decrease by the same amount in this case because this system is equimolar. So I cannot say that the forward reactions is going to be affected more because the forward reactions use more particles, or the back reaction is going to be affected more because it uses more particles. Since the forward reaction uses 2 particles, to make the products, and the back reactions also uses two particles, the forward and back reactions will go down by the same amount. But because they are going down by the same amount, the system is still at equilibrium because the rate of the forward and back reactions are still equal to each other. So the system just remains at equilibrium. Therefore, it is not going to respond to this change by shifting more to the right or more to the left. So an equimolar system doesn't respond to a change in pressure because when you change the pressure, you haven't taken the system out of equilibrium. So it's just going to stay at equilibrium. But notice how the rate of the reaction of the system has to be lower because ultimately you have decreased the pressure. So that should reduce the rate, but has no effect on the position of equilibrium. All right, let's talk about the last two changes, which are temperature. So if I increase the temperature, the response is to go towards the endothermic side to try to absorb some of that excess heat. And this is what the concentration time graph will look like. Now, if we talk about a rate over time graph, so once again, before the change, system is at equilibrium. If you, oh, that's supposed to be an increase. Okay, increase. I'm going to change this in the note. So increase, that's an increase. Let's hope that I got the rest correct. So if you increase the temperature, that is going to increase the rate of both the forward and back reactions. Temperature will always increase reaction rate, no matter what. No matter whether the system wants to shift forward or back, the rate of that system will increase. However, the back reaction is going to benefit more from this change because the back reaction in this case is endothermic. So it normally requires temperature. It has to absorb heat anyway. So the rate of the back reaction is going to increase more as a response to this increase in temperature. So the forward reaction go up like that, but let's say the back reaction has its rate go up even more. Now, as the system is going to shift backward to respond to this change, and then once again, you're going to have the rate of the forward reaction increases as the system shifts backwards, and the rate of the back reaction it decreases as the system shifts backwards. I think the response is pretty much either the system shifts forward or the system shifts backwards. It's really just how the rate changes when the change is applied that you really need to think carefully about. And then equilibrium is reestablished as the rate of the forward and back reactions equals to each other. And this rate has to be higher than the original because you have increased the temperature, so you should have a higher reaction rate than before. So that's increase in temperature. Now, if you look at a decrease in temperature, let's hope this is, yeah, I think that's the correct graph. So if you decrease the temperature, the system will shift towards the exothermic side, which is, in this case, the forward direction. So if you look at a rate over time graph, so before the change, systems at equilibrium. Now, if I decrease, oh, I think what I did is I just mix up the text here. I think I did some copy and paste, and it doesn't work too well, so that's a decrease. I'll make sure I change it for the PowerPoint. Okay, so if you decrease the temperature, that would decrease the rate of the forward and back reaction. But the back reaction will be affected more because the back reaction is already endothermic. So if you decrease the temperature, that is going to slow it down even more. Okay, so what is going to happen is that the forward reaction will experience a sharp decrease in reaction rate, but the back reaction is going to experience that even more. And then as the system responds by shifting forwards, you're going to decrease the rate of the forward reaction and increase the rate of the back reaction until equilibrium is reestablished and the rate of the forward reactions and back reaction are equal to each other again. Now, this rate has to be lower than the original equilibrium rate because ultimately you have decreased the temperature and that is supposed to reduce reaction rate. Okay, so that's all 6 changes. I hope I haven't completely confused everyone, though I have a suspicion that I have. But I still want to talk about the addition of a catalyst, which was one of the questions in the worksheet. And we have said that a catalyst is not going to affect equilibrium because it doesn't change the concentrations of anything. And you can also reflect the effect of a catalyst using a rate of a time graph. So before you add a catalyst, this is the rate of the forward and the rate of the back reaction. And if you add a catalyst, that is going to increase the rates of both the forward and back reactions, but they will increase by the same amount. And the reason, well, one way to look at this is if you use an energy profile diagram. Okay, so we have, let's say, this is N2 and 3H2. And then, so I'm going to draw an energy profile diagram of the forward direction. So this is the activation energy. This is activation energy of the forward reaction. And this is the activation energy of the back reaction. If a catalyst is added, what a catalyst does is that it is going to lower the activation energy required. So it's going to lower the gap to get to the transition state. So basically, if I add a catalyst, it's going to lower this peak. So this is with catalyst. So you can see that it is going to lower the activation energy for both the forward and back reactions. So this is going to be the new activation energy of the forward reaction, and this part is the new activation energy of the back reaction. So both the forward and back reaction will have an increase in reaction rate when a catalyst is added. But it's by the same amount, so the system just remains at equilibrium. This is why it doesn't respond to an addition of a catalyst by shifting forward or back. And that is it for this video.